Hello everyone, I'm Ruoxu.
I'm
Hello,
Junyu Huang.
I'm Erik Novak.
Yeah, today we are going to talk about stochastic calculus with jumps. So recall that our lecture starts by considering dynamics with random noise. Okay, and we consider noise with some good properties that are first, the increments are independent, which means if you have disjoint time intervals, then the increase in these intervals are all independent. Second, we have stationary increments, which means for any time interval of the same length, their increments should be following the same distribution. And third, we want the noise to be continuous in time. So such a good noise turns out to be a Brownian motion. So this is what we studied in lecture. And now for some purpose, sometimes we also want to study noise with jumps. So for this purpose, we can consider a slightly weaker properties. That is, instead of continuous in time, we only require it to be continuous with property 1. Okay, then this noise might have jumps, and we can always choose a version of such a noise to be right continuous with left limit. And such a process is called Levy process. So let's first look at the simple case of Levy process. This is a Poisson process. And it is a counting process starting from 0 and takes integer values. And the increase from time s to t will follow a Poisson distribution of parameter lambda times t minus s. Okay. So recall that Poisson distribution is a distribution taking value in integers. So this is modeling the occurrence of an event over random times. And so it's coming one at a time. And the time gap between two occurrence will follow an exponential distribution. Okay. So the increments will be independent. So this is a good case. Now, if recall that this will assume this is our familiar Ito process, and this has no jump. But if we want to add some jump like this suspicious form, d of nt, then what will happen? Well, we get such a new path where when nt have a jump, we also have the same jump in the path of xt like this. So we get a random stochastic process with jumps. And in general, this will be what we want to study, but this is still not the complete story because here the jump steps are always 1. But in general, we want to study process with different jump steps. So this will be modeled by a compound for some. Okay, so in a compound for some process, it's like Poisson process, but instead of jumping by step 1, each jump size will follow another distribution z. And because we have stationary increments, each jump size will be the same. They have same distribution. Okay. And this yt is just sum of NT-IID random variables following z. Now we have this will be a more general Levy process. We can define integral like this form of phi over a random process yt. And this can be understood in a similar way, that is first define this for elementary functions and then take limit to a square integral functions. But formally, such an integral should be defined by a Poisson random measure. That is, this is actually a double integral, first over time dt and second over the jump size of dx. And I will ignore here for simplicity. You can look at some more formal definition in the appendix. And then we can also extend Ito's formula to like Levy process. So for simplest form, let's look at a function on Poisson process nt. Then this difference is counted by the integral of difference of f of ns minus f of ns left integral left limit times dns. So this difference here will be 0 if ns is continuous at s, and when ns is not continuous, there is a jump. So this difference will count this jump in function value f. So the integral is actually a sum of these jumps. And for a more general form of our ETL process, we can see the ETL formula will have a similar form as we learned in class, but it has an additional term to count the sum of jumps. And again, for a more general form, look at our appendix.
Okay, I will start with my part, and I'm a student from biostatistics department, so my concentration will be on the application in survival analysis, which is like a big area of my major. First, I will discuss what is a survival analysis, and I have to make to have an example. Like, suppose we want to know the effect of a medicine on the relapse of certain cancer, and we do a clinical trial. So we randomly assign patients with placebo or the medicine, and we record the time passed until the relapse. And the proportion of patients that haven't experienced the relapse is called survival probability. Clearly, it's a function of time t. And the biggest challenge in this trial is that there's a censoring data in the experiment. Censoring data means that the patient's true relapse time is not recorded. This may arise from various reasons. For example, failing to follow up during the trial, and the patient's deciding to quit the trial, or the trial ended before the relapse. So instead of the true exact relapse time, we will record a time that the patients haven't experienced the relapse. And our main problem is to estimate the survival function with these data. And here are the three terms. First is called an event, and means the end point of the trial for a subject. In the example, it is relapse. And another term is survival times, which means the times to the occurrence of a given time. And censoring means some subjects are not observed for the full time of failure. And the plot on the right gives us a good example of what is happening when we are doing an experiment, clinical trial. And we can describe the whole story with counting process. And a counting process is the stochastic process, which start from 0, and the time the NT is always less than infinity, and the path is right continuous, piecewise constant, and have jumps of size 1 only. And let t denote the event time, and u denote the censoring time, and of one patient. So we can only observe the minimum of t and u, which is the observed time. And we can use two counting processes to represent the status of this patient. The first is the indicator function of x less than t, and capital T less than or equal to capital U, means that the patient experienced the event before time t, and the capital N ut, which means that we observe the patient has been censored before time t. And the sigma algebra generated by these two processes contains all the information of the patient's history. And these two processes are either 0 or 1 at each time point, since it only represents the status of one patient. And clearly, we can see that NT is a submartingale with respect to the sigma algebra. So by Duke-Mayer decomposition, there exists a unique increasing right continuous process, A adapted to FT minus, to make M equals to M minus A, a martingale. And the explicit expression of it can be found. First, we have to we assume ST, the capital ST, is the survival function. It's 1 minus the CDF, and FT is the PDF. And we define lambda t as in this form, and which is called a hazard function. And we can derive A in this form, which is the integration of a process times the hazard function, and to make M a martingale. And the key question is how to estimate the survival function on the hazard function with M given with the observations. For simplicity, we assume that the time t and the censoring time u are independent. And we let NIT denote the counting process of the ICE patient, and NT equals to the sum of the NIT be the sum of these processes, and YT equals to the sigma I indicator function xi greater than or equal to t, which means that the patient is at risk at time t. A very intuitive idea to estimate the survival function is called Kaplan-Meier estimation, which is the product of the 1 minus delta ns over ys. The delta ns over ys is just the proportion that proportion of patients that experience the event at time s. So 1 minus that is the proportion that the survival proportion. So when we have this product, this estimator is exactly the proportion of observations that haven't reached the event at time t. And as a statistician, we not only care about the point estimation of the survival function, but also a confidence interval, which means we have a range of the estimation. I mean, we should estimate the standard error of this estimation. So we should derive the sampling distribution or asymptotic sampling distribution. And the result is given below. Like we can see that the S hat t is a Kaplan-Meier estimator and ST is the true survival function, and the difference of the times square root n converges to transform the Brownian motion. And the sigma square t also has a consistent estimator called VT in this form. And with this distribution, we can develop methods to test the difference between different survival curves, and there are more stories to go.
All right, and I'll be giving a presentation on a different way to apply the idea of jump processes to get better information and more accurate modeling. So what I'll be presenting on is the jump diffusion Cox-Ingersoll-Ross process, the model of the effects of primary shock events in default intensity. Now, the Cox-Ingersoll-Ross process is related to the idea of credit risk. And the idea of credit risk is closely associated with default risk, which is the risk that some firm or some company that's being modeled, it will default on their payments. So they'll be unable to pay. And we're also able to model the interest rate of a variety of different derivatives. In this case, derivative means some financial instrument or tool that was created based on the idea of the credit risk. And so we're also able to model what the interest rate of those financial instruments ought to be from the default risk, the underlying default risk of the firm. And there are many models that are used for this purpose, one of the most common of which is the Cox-Ingersoll-Ross model. It's a one-factor model, which means that you kind of package all of the risk into one market risk, one general market risk, which is given by some Brownian motion. So as we can see, this is the structure of the Cox-Ingersoll-Ross process, and it has some very interesting properties. So first of all, it's the sum of the squared Ornstein-Uhlenbeck processes, which is just an interesting situation, and it's somewhat reminiscent of the idea of how chi-squared is the sum of the squared normal processes. It's also ergodic with stationary distribution, and unfortunately, it doesn't have any closed form solution, which you might think is a weakness, and indeed it is, but it has certain important properties besides, despite not having a closed form solution that compensate for this particular weakness. Specifically, if we consider y sub t, our process, as the interest rate or the risk of defaulting, then what we have is that the process converges to a mean that's given by the eta value here. So in time, it'll converge to that mean, and lambda is the speed of adjustment to that mean. So this is how the variables of the drift coefficient kind of behave in this respect. And the standard deviation factor of theta, it will ensure that there are no negative interest rates supposing that both lambda and eta are positive. And this is one of the biggest strengths of the model relative to other processes. It does not allow for negative interest rates, or if you're measuring the risk of default for a negative risk. So how does the CIR process behave when it's close to zero? Generally speaking, suppose it's only slightly greater than zero, then the standard deviation is going to become extremely small, which dampens the effect of random shock given by the Brownian motion on rate. Which means that the process ends up being dominated by the drift term. And the drift term, as we saw earlier, pushes it back toward the mean. So essentially, the smaller the standard deviation, which happens the closer it is to zero, then the more influence the drift term is going to have on the process, pushing it back to the mean. And specifically, the way that this behavior happens is that if theta squared, which is the standard deviation factor, if theta squared is less than or equal to 2 times lambda times eta, the drift term, it'll drive the process away before it gets too close to zero. So before it gets too close to zero, it's driven away. However, if theta is greater than or equal to 2 times lambda times eta, the process might occasionally touch zero and reflect. Nonetheless, it'll never go underneath zero, which is the behavior we're interested in. So now that we understood what the Cox-Ingersoll-Ross process does, it's important to note one of its limitations. And to understand that, we should consider what a primary shock event is. And this is basically some external event that ends up leading to a jump in the firm's default intensity, its likelihood of defaulting. And what are some examples of primary shock events? These might be some sort of government fiscal or monetary policy that's detrimental to the firm's financial wellness, or some release of corporate financial reports that might have not great information for the company, maybe some quarterly earnings report. Might also be a natural disaster, some sort of maybe a hurricane destroyed the firm's warehouses, or perhaps a terrorist attack. And what ends up happening then is that the risk that the firm defaults obviously grows. And the process after this immediate jump, because it does happen immediately, then the process will decrease back to some mean as the firm attempts to avoid bankruptcy and generally restabilizes itself. And this will happen until some other shock eventually occurs again, because the life is unpredictable. These shocks are essentially bound to happen. The Cox-Ingersoll-Ross process does not model these shocks particularly well. So what we do to counter that is we add in a jump diffusion modeling scheme to the Cox-Ingersoll-Ross process. And to do that, we consider that J sub t is some independent compound Poisson process of jump intensity L, and whose jumps are independent and exponentially distributed with mean mu. And we want those jumps to be positive, so the mean should certainly be positive as well. Now, the way for this to be well defined is lambda times eta is thus greater than or equal to zero, and as mentioned, the mean should also be greater than or equal to zero, so the process is well defined. And then what we end up having is the basic Cox-Ingersoll-Ross process with jump will solve the following SDE. Now, we might have some extra details in the coefficient for the d of J sub t, but this is the basic version. We simply add the Poisson process here, and this allows us to model jumps. Now, it has a few attractive properties, the jump diffusion version of CIR. In particular, the moment generating and the characteristic function are both well known and relatively easy to work with. So they're all equal to e to the power of q in the moment generating function case times the integral from 0 to t of the process, or in the characteristic function, it's e to the power I times u times the same integral as before. And finally, in much the same way that the Cox-Ingersoll-Ross process is able to give us certain very important quantities and behaviors, the Cox-Ingersoll-Ross process with jumps is equally able to do that. Unfortunately, the details of this extend beyond the scope of this of this presentation or its appendix, but I encourage anyone to read the paper that I originally referenced to write this section to get some of the details on how to calculate these quantities. But for example, we have the survival probability of the firm after a specific amount of time. So what's the probability that the firm did not default ever after a specific time t? This is something that we're able to calculate. We're also able to calculate the probability density function of defaulting at a specific time t. So this would be not just the default risk, which is just a number, but really the probability density function of defaulting as a whole at that particular time. And this also allows us to find the ideal value for certain specific financial instruments, like the pricing of the default zero coupon bond, or what the fair premium would be on a credit default swap, the latter being the credit default swap, also known as a CDS, meaning as the when two traders switch a risk derivative, what would be the premium on doing this switch? So we're able to calculate all these quantities using the jump diffusion Cox-Ingersoll-Ross process as well. Well, thank you so much. Thank you so much for our presentation. I hope you enjoyed it.